just about any time you have a problem dealing with forces and accelerations, the thinking process is almost always the same. And it goes something like this. Let's just imagine a pretty simple situation just for starters. So there's a skydiver, and the skydiver has opened the parachute, and the purpose of the parachute is to create a really, really big drag force. The skydiver is moving this way, so the drag force points opposite to the direction of motion, so that's a big strong force pushing backwards on the skydiver. That's going to slow them down, make the skydiver accelerate a lot less than would have been the case otherwise. And we would like to know exactly what that acceleration is. If there were no drag force, then the only force on the skydiver would be gravity. In other words, the skydiver would be in free fall, and the acceleration of the skydiver in free fall would be pretty big, 9.8 meters per second per second. That is, the skydiver would be moving 9.8 meters per second faster every second. So, to figure out what the acceleration is, the first thing you do is not think about the acceleration. Instead, think about the forces that would produce that acceleration, and ask the same kind of question that you did for a lot of the exercises in class yesterday. What forces do we have in this situation? And then draw a free body diagram to show those forces. The only two forces in this case, there's weight pulling down on the skydiver and parachute, and then the drag force pushing up, pushing backwards on the skydiver. This cancels out most, but not all, of the weight. One thing we know is that the drag force gets stronger when speed increases. So the skydiver falls and speeds up. As the skydiver speeds up, the drag force gets stronger and stronger until, let's say, at one moment in time, the drag force has increased in strength so that at this moment it's equal to 80% of the weight. Like the magnitude of the drag force equals 80% of the weight, 0.8 times the weight. So the weight is still a little bit stronger than the drag force. That is, the downward force is still stronger than the upward force, so this upward drag force doesn't cancel out all of the downward force. There's still a little bit of downward force left over to supply a net force down. The skydiver is still gaining downward velocity. The skydiver is still accelerating with a downward acceleration. And we want to figure out exactly what the size of that downward acceleration is. Okay, so in a free body diagram, you want to identify the forces and the directions of those forces, and you want to be clear what the direction of the net force is when there is a net force. And you also need a coordinate system. You have to know which way is positive and which way is negative. Customarily, we like to put the direction of motion in the positive direction. Skydiver is falling, so down will be the positive direction. That's important because the next step is to write an algebraic statement, write an algebraic expression that shows how these forces combine and to produce a net force. How those forces get added together to produce a net force. In other words, an algebraic statement that says net force equals some combination of the particular forces that you identified in the free body diagram. And the basic rule when you're writing out this algebraic statement showing what the net force looks like in this particular case, the rule is pretty simple. Just add all the forces in the positive direction and subtract all the forces in the negative direction. Well, the only force in the positive direction is weight. The only force in the negative direction is drag force. So here it is. you add in all the positive forces and subtract all the negative forces, and that's what the net force consists of in this particular case. And then being a net force, Newton's second law tells us that that must be equal to mass times acceleration. And acceleration is the thing we need to find. So the next step is to rewrite weight in terms of other things that we know. Weight is always mass times g. We know what g is. It's the acceleration due to gravity, 9.8 meters per second. And we know that the drag force is just equal to 80% of the weight. So the weight mg minus 80% of mg, because mg is the weight, that's the net force, so it's equal to mass times acceleration. But there's an m in every term here in this equation, so we can cancel it out conveniently. We didn't even need to know what the skydiver's mass was in this particular case. And so all we're left with is g minus 0.8 g. That just gives us 0.2 g. And that's equal to the acceleration, which is 1.96, or approximately 2 meters per second. Instead of the free fall acceleration, where the skydiver is gaining 9.8 meters per second of downward velocity in every second, the skydiver is still speeding up a lot, but only 2 meters per second faster in each second. Now, the process here is the same. You follow the same process in any other question, including ones that are a lot more complicated than this. And there's basically just 3 steps to the process. Draw a free body diagram to identify all the forces and the directions of those forces, and identify the direction of the net force, if there is one, or state clearly that there is no net force if that's the case. And then write down something that shows what's the positive direction and what's the negative direction of your coordinate system. It's important to write down all of those things so that you don't have to keep them in your head. As I've said before, there's actually very limited space in your conscious mind, and you don't want to take up that very limited space with things that could just as easily be recorded on paper. The next step is, just like I did over there, write down the expression that shows how the forces you've identified here combine to give you the net force. And then the third step, make any substitutions that you need to make. Set this algebraic expression equal to mass times acceleration. Make any substitutions that you need to make, such as substituting mg for weight, right? Anytime you've got a defining equation for a particular force, like you do here, mg is the defining equation for weight, write it out in this more detailed form. Don't just leave it like this. Use everything you know and write out the defining equation for any particular force that you know about. and then solve that equation. Right, once, when you're at this point, you've figured out one side of the equation. Then you set it equal to mass times acceleration because you figured out what the net force looks like. Now you've got both sides of the equation. Now you can solve that equation for whatever it is you need to find. So let's look at another example. Let's say I'm pushing on a crate, and the crate is on a pallet that has wheels on the bottom. So there's this crate and then wheels, and the wheels are rolling just like normal. And I know that my push, I'm pushing with a force of 400 newtons. And I know that this whole thing here, crate plus pallet and wheels is 80 kilograms. And somebody has measured how the crate and I are moving, and they determined that our acceleration is 0.2 meters per second per second. All right, the crate and I are speeding up as we move this way, and in every second we're moving 0.2 meters per second faster than we did in the previous second. And I'm pushing this way in the direction of motion. And since I'm speeding up, we know that acceleration points in the same direction as velocity. Acceleration points in the same direction as velocity whenever something is speeding up. And I'd like to calculate what the force on the wheels is like. The wheels are rolling, so we know there's rolling friction. I'd like to know how big that rolling friction force is. So, what do I do here? First thing, be clear about what all the forces are that are acting on that crate. Draw the free body diagram. So, of course, there is the weight, gravitational force from the earth pulling down on the crate, and then there's a normal force from the floor pushing up on the crate. And then there's another normal force, the horizontal push from my vertical hands, vertical surface pushing horizontally, like a surface pushing in the perpendicular direction, that's a normal force. Normal force from hands on crate. And then there's a backwards force. That backward force is the rolling friction force. Because I know that if these wheels weren't rolling, they'd slide. They would slide this way. But rolling friction prevents the sliding and makes them roll instead. So if the rolling friction is to prevent sliding this way, the rolling friction has to point the other way in order to prevent sliding this way. And I'm speeding up in this direction, the acceleration is in this direction. Net force always points in the same direction as acceleration. So the net force is that way. And again, let's set up a coordinate system where the direction of motion is the positive direction. Like that. So that's the free body diagram. The next step take the forces I've identified and show how they combine to give you a net force. Well, first of all, the two vertical forces combine to give you no force at all. Since the cart is moving only horizontally, you could then say that the vertical velocity is always zero. Even more important than saying that the vertical velocity is zero is to note that the vertical velocity is always zero. The vertical velocity is constant. Constant velocity means that the rate of change in that vertical velocity is zero, no change at all. Rate of change of velocity is acceleration. There is no acceleration along this direction because the motion along this direction is always the same. Specifically, always no motion at all. But that means zero acceleration vertically, which means zero net force vertically, which we already kind of knew. The net force was entirely horizontal. It had no vertical component. But this net force then is just all the force in the positive direction minus all the force in the negative direction, which is normal force from my hand on the crate. That's the force in the positive direction, minus the rolling friction force. That's the force in the negative direction. And being a net force, it's equal to mass times acceleration. And now I can solve for the size of the friction force because I know all the other numbers. I can substitute in for those numbers. This was 400 newtons. That's what we're trying to figure out. Mass was 50 kilograms. And the acceleration was 80 kilograms. And the acceleration was 0.2 meters per second. So we've got 400 newtons minus the friction force. 80 times 0.2 is 16. 16 what? Well, this is a mass times an acceleration. And Newton's second law tells us that a mass times an acceleration is force. So that's 16 newtons. So in other words, my pushing force is 16 newtons bigger than the backwards pointing rolling friction force, which means rolling friction has a magnitude of 384 newtons, or rounded off to 380 newtons, since we only have 2 digits of information here in any of our inputs. But notice, I did all the same things as I did in the previous problem. Those 3 steps right there. Now, one last example that's a little more complicated because it'll have deal with forces that aren't just vertical and horizontal. We'll have to look at the vertical and horizontal components of that force. Okay, so I'm pulling a wagon. And the mass of the wagon is 20 kilograms. And the handle of the wagon is pointing that way, and I'm pulling on it. 100 newtons of force for my pull. And I'm pulling just right so that it's moving at a constant velocity. And in that case, I would like to figure out the values of all the other forces that are acting on the crate. I know the magnitude of my pulling force, and if I know that the mass is 20 kilograms, I can figure out the weight. I want to figure out all the other forces as well. Let's say here that I know that I'm pulling at a 30-degree angle. Right. To say that I know completely the pulling force means that I have to know both the magnitude and the direction of the pulling force. I want to figure out the other forces. What are those other forces? I'll answer that question by drawing a free body diagram. So the other forces are the weight, and then a normal force from the ground pushing up on the wagon, and then tension in this handle that I'm pulling on, and in turn that handle is pulling on the wagon. And then again, just like in the previous case, there are wheels that are rolling, so they've got a rolling friction force. Just like in the last case, the wheels are not sliding that way, they're rolling instead. So to prevent sliding that way, there has to be a rolling friction force in the other direction. So I know all about that. I can calculate that very easily. The two trickier forces that I need to calculate are the rolling friction and the normal force. But just for completeness, I want to know which way is the positive direction. I'm pulling the wagon that way, so I'll say that positive is the direction of motion, negative direction is opposite to the direction of motion, and the velocity is constant in this case, which means there's no acceleration, which means there's no net force. If there were a net force, there would have to be acceleration. So in this case, net force is 0. When we say that the net force is 0, that means the magnitude of the net force must be 0. But you can calculate the magnitude of any vector, like net force, by looking at its components. Just do the Pythagorean theorem again. The magnitude of net force is just square root of sum of the squares of the components. The sum of the squares of the two components, take the square root of that, will give you the magnitude of the vector itself. But if the magnitude of the vector itself is 0, and it can be 0 only if both of these components are 0. Obviously, if either one of those components is not 0, then the magnitude is not 0. So the x component of the net force is 0, and likewise the y component of the net force is 0. And that's what allows us to figure out the other forces. In this case, we go to the next step here and write down an algebraic expression that shows how forces combine to give you the net force. We have to do that twice. We have to show how forces or their components combine to give you the net horizontal force, and that's going to add up to 0. And we have to show how forces and their components add up to give you the net vertical force, and that'll add up to 0 also. So let's do it for the horizontal direction first. So net force in the x direction. Again, all the force in the positive x direction minus all the force in the negative x direction. All the force in the positive direction is the x component of the tension, the 100 newtons of tension pull. So we have to calculate that first. 100 newtons, and then here's the x component, and then here's the y component. This 100 newtons of tension is what you get if you have this much pull in the x direction plus this much pull in the y direction. And if this is 30 degrees, what is the x component? Well, the x component is adjacent to this 30-degree angle, and whenever we're trying to calculate a triangle side that's adjacent to an angle, we use cosine. So Tx equals hypotenuse times cosine. That's the rule. 100 newtons times cosine of 30 degrees, and that comes out to about 87 newtons. So that is the forward pointing positive force along the horizontal direction, along the x-axis. That's all the force in the positive x direction. All the force in the negative direction, x direction, is simply the rolling friction. And being the net force in the x direction, that's going to have to equal mass times whatever acceleration you might have in the x direction. But it's moving at a constant velocity, so there isn't any acceleration. That's 0. 87 newtons minus the rolling friction force is 0, which means the rolling friction force itself is also 87 newtons. Now we need to figure out the vertical forces. Do weight first, that's the easy one. Weight is just mass times g. And the mass of that wagon was 20 kilograms. And then g is 9.8 meters per second. So that weight then comes out to 20 times 9.8, or 196 newtons. Now, the one force that we still have to figure out is the normal force here. And we can do that by just going through the same process again. Using the free body diagram, use that as a guide to write down an expression that shows how forces or components combine to give you the net force along the vertical direction. So net force in the y direction is all the force in the positive y direction minus all the force in the negative y direction. Two forces in the positive y direction, normal force, and then the vertical component or the y component of tension. Right? This 100 units of tension was really the same as this much tension pull in the positive x direction plus this much tension pull in the vertical direction. We'll just, for the moment, we'll just call it the y component of tension, which is pulling in the positive y direction. Positive force, so you add it in. And then the one negative force, the one force in the negative y direction, is the weight. And of course, being a net force, it's equal to mass times acceleration, but the velocity is constant, so there is no acceleration. So what we have is normal force plus y component of tension minus weight equals 0. We need to figure out what this is. There's our 100 newtons of tension pull, and there's the x component, there's the y component, there's the angle that we're using. The tension pull points 30 degrees counterclockwise with respect to the positive x-axis, and the y component of tension is opposite to this angle. So if we're trying to figure out the length or the magnitude of a side that's opposite, we use sine. Sine is the ratio of opposite divided by hypotenuse. So Ty is just hypotenuse times sine, or 100 newtons times sine of 30 degrees. Sine of 30 degrees turns out to be 1/2. So 100 times 50, that 100 times 1/2 gives us 50 newtons. Well, that number is 50 newtons. And we had figured out earlier that the weight is 196 newtons, so now we can find out what N is. N plus 50 newtons minus 196 newtons equals 0. Or N, add 196 to both sides, subtract 50 from both sides, so that now on the left-hand side you've got only N. And the normal force then is 146 newtons. Now notice that in a lot of cases it'll turn out that the upward normal force is exactly equal to the downward weight force, but that's not true in this case. In this case, the upward normal force is less than the weight. That's because the upward normal force isn't the only upward force that's trying to cancel out the weight. In trying to cancel out the weight, the normal force gets some help from the upward vertical component of the tension. So since the net force is 0, that means the total upward force has to equal the total downward force. The total downward force is just 196 newtons of weight, but the total upward force is normal plus the y component of tension. Those two forces together have to add up to 196, so the normal force doesn't have to match that 196 newtons of weight all on its own. It gets 50 newtons of help from the upward component of tension. Okay, and as I said, and as you'll see when you work through more of this stuff in class, every problem involving forces and accelerations should be worked the same way. Should be worked the same way because this is a method that you know. This method is there. You can always use it, meaning you will never be in a situation where you don't know what to do. Ordinarily, when you're first given a problem, you have no idea what the answer is, but that doesn't matter because you know what to do. You have a method that will quite likely get you from your question to the answer.